A steel pipe is being carried down a hallway 9 feet wide. At the end of the hall, there is a right-angled turn into a narrower hallway 6 feet wide. What is the length of the longest pipe that can be carried horizontally around the corner? This problem is a difficult optimization problem, but it can be easily solved using the following method. We can draw line segments that are parallel to the walls such that two right triangles are created. We can now use geometry to find out the other angles. This angle must equal 90 minus theta due to the triangle sum theorem. Using the corresponding angles postulate and alternate interior angles theorem, we can find the other angles as shown. We can now split the two parts of the pipe into L1 and L2, where the total length of the pipe will be L, or the sum of the two. Now, using trigonometry, we can find the length of L1. The cosine of the angle 90 minus theta will equal to 9 over L1. Rearranging this, we get L1 is equal to 9 over cosine of 90 minus theta. Using trigonometric identities, we can say that this is 9 over sine theta. Now let us do the same for L2. Using alternate interior angles, we say that this angle is equal to theta. Thus, the cosine of that angle will equal 6 over L2. Rearranging gives L2 is equal to 6 over cosine theta. Therefore, adding these two lengths gives us the equation for L. We now must differentiate this in order to find the maximum length. Using the first derivative test, we can differentiate L and set it equal to 0. We can differentiate the equation as follows. Now we get this equation with just sine and cosine. We can rearrange this to 9 cosine theta cubed is equal to 6 sine theta cubed. By simplifying, we can get tangent theta cubed is equal to 3/2. In order to solve theta, we get theta is equal to the inverse tangent of the cube root of 3/2. We now use this value to substitute into our original equation for L. We can now use a calculator to solve this value. The answer that we will get is 21.07 feet.
Let us try this new problem. Find the largest possible volume of a right circular cylinder inscribed in a sphere of radius r. Pause the video if you would like to try this on your own. We can first start by drawing a simple diagram. The radius of the sphere is equal to r. Because the cylinder is inscribed in the sphere, the diagonal of the cylinder will be r. We can let the height of the cylinder equal h. We can then use the Pythagorean theorem to solve for the radius of the cylinder. The derivation is as follows. We must leave this value in terms of r and h, because they are the constants in this expression. The formula for the volume of a sphere is pi r squared h. We can now directly substitute the value that we got for r squared, or the radius of the cylinder. This is why we did not have to apply the square root, since it is not needed. Now that we have our expression for volume in terms of one variable, which is h, we can then differentiate the expression. Because h is our only variable in the expression, we can treat pi and r as constants. Because we have to find the maximum volume, we must set the derivative equal to 0 and solve for our variable. The value that will be obtained after solving will give us our desired height of the cylinder. We get h equals 2r over root 3. This is our desired maximum height. We can then substitute this value into the original expression for volume. We cancel the 4 in the above expression, so we get r squared minus r squared over 3 in the parentheses. We can subtract these two values and cancel like terms, so we get 2r squared over 3. Finally, we can multiply out all the values to get 4 pi r cubed over 3 root 3. This was a fun problem to solve.